So in our previous class, we managed to refer to the strain energy as we are still on our strain energy, but that was working with the suddenly applied loads. In this case, we are going to notice that we have got the shock loads. And that can also be referred, these shock loads that we are seeing here can be referred to as the impact loads. So it can be referred to as the impact load, the shock loads. That it can be from the word itself, impact, meaning to say this time the object, when it is being taken from one point to another, there is going to be an impact. There is going to be an impact. Remember, when we talked of the suddenly applied loads, I referred that it is one which the full force is applied instantaneously, not gradually. It will be instantaneously, but there is no impact. That was what we had when we were dealing with a suddenly applied. When we're working with suddenly applied loads, we saw that there was no impact. There was no impact there. Meaning to say the height was equal to zero. There is no height at all that the object is going to be moved to have that impact. There was no height at all. So when you're referring to the calculation of the strain energy, you were just using your formula that the strain energy can be calculated from what? Half times the force times what? Times x. Extension. This is what we had. As we had this, it is because of the height that was equal to zero. There was no movement in terms of the material, in terms of the load that is being given. So we did not notice even the effect of that height. But okay, what will be the effect of this height? Because now there is an impact, meaning to say the load is going to fall at a certain height in order for that to have an impact. It must fall from a certain height to have the impact at the ground with the ground, which is given as the collar onto the collar of the diagram that will be given, which is the bar, the single bar that you'll be having there. So let me explain this way so that we can understand each other. Let's say we are considering this shock loss to single bars, and you are given something, a vertical bar. Let us just consider a vertical bar, which is actually being rigidly attached. This one is rigidly attached to the top end. Okay, let us just say we have got something of that nature, and it is attached to the top rigidly, and there we've got have a certain mass, which is our load, right? So let's say we also have mass, which is actually, we're going to consider this part as our load. And the mass that we are given, or the load that we are given, falls for a certain height onto the collar. So it's going to fall a certain height to the what? To the collar. Okay. So this is what we have in that case. It must be exactly in contact. Let's see if this is going to be able to work. All right. Something like this case. Okay. It's not supposed to have a gap there. So it falls to the collar at a certain height from where it was here. It falls at a certain height onto the collar. As it does that, because of the impact, because of falling to this collar, it will cause an extension. That will cause an extension. This load, it has fallen here. So it is going to cause an extension. So let us just save the part of what? The extension. So we're going to just have something like this. All right. So let me present that way. As it has fallen there, it will cause an extension. So the extension is now from where it was here up to here. This is our extension of the what? We're talking of the extension of the what? The bar, this one, the bar. This bar is the one that you're extending. So it's going to have an extension from where it was. It was ending here. Remember, this was your bar ending here. So the extension is going to start here to this. This is our extension, this one, this part, from where it was to that length, this one, the wall of it up to this point. So this will be your extension, which is being caused by what? By the load as it gets to the impact, as it has an impact with what? With the collar. So this is the characteristics that we're actually going to talk about. As we can see now, there is a height fallen. And as we talk of the height that is being fallen, we definitely think of what? Potential energy to be lost. Think of both of that. The height, now we have that. It's different from the previous case where the height was 0. No, this time we have it. So this is the idea, guys. Okay, let me just try to paraphrase what I was stating there, so that for in terms of understanding or the notes that we're going to have. So like I was saying, and this part that we have there, this presentation, we have got a vertical bar. Okay, so we're going to say the vertical bar is rigidly, meaning to say it is like the attachment that we have there, guys. There's not going to be any movement there from where it was. It's going to be rigidly attached at its top. At its top. And also has a rigid collar and has a rigid collar. That is the collar there. Okay. At its lower end. At its lower end. So this is what I'm trying to say there. It has collar already. The height is fallen onto the collar. Then from the collar that we are having, an extension is made. How? Because of this mass. So in this case, a load, which is our mass, okay, falls. So this load falls from a height. From a height, which is this height h, onto the what? Onto the collar. Okay, so as it falls, it's going to fall onto this collar, onto the collar, which is the one at the lower end. Okay, this is A there. Okay. So as it falls onto the collar, we saw that it causes what? An extension there. It causes an extension X. So that's causing an extension. Causing an extension X. So if now there is an extension that has been made, what does it mean? It means the total distance the mass has fallen is h plus x. Because it caused an extension. So it means it's going to go down up to this. Well, remember, it was here. So this extension, it means it's going to be now affected to this ground. So the height now affected by the mass is from this point that it had plus the extension. Remember that. So we're now talking of what? The total distance. So to such a way that the total distance is going to be equal to what? H plus X. You have to add H plus X. This is the total distance which the mass has fallen. Okay, the total distance, the mass has fallen. So with this understanding that mass has fallen from H and also an extension of X, so H plus X. This is the major characteristic of what you're seeing here. So how is this going to help us in the calculation, this and that? All right, remember your bar, originally it will be having its own length. This is our bar that we are given here. So originally, we do understand that it is going to be taken at a certain length, which is the original length of the bar. And also definitely this is the bar where we can also be given its diameter. So you can also be given the diameter of what? Diameter of the bar, this and that. Remember, for those areas, as long as we talk of this extension, remember we talked of that extension when we're talking about strain. I mean, the part of stress and strain, we had that extension. So do not forget your formulas. You still need those formulas. Strength of materials, it's a continuation from the first formula that you had. You're not supposed to forget any formula because they continue like that. All right, anyways, let's see. So due to this, because of the height that is fallen, which is, I mean, this total distance, which is H plus X, you are going to notice that in terms of the calculations, they can ask you to calculate anything in terms of this, but what is important from the statement or from these shock loads on its own like this, when you're just given a single bar, it is on the energy. Formulas or calculations can be made when we consider the energy. How so? So from the energy, let's see what's going to happen. As this object is falling, it's lost potential energy because potentially it was having its energy. So we are going to notice that there will be a loss in potential energy. And that loss must be as an equivalent of a gain in strain energy. Strain energy. So this can give us a formula now because we know our potential energy. Remember from your science, guys, potential energy from what? mgh. But we no longer use mgh as it is. Why? Because the height, the distance that the mass has fallen, it is now h plus x. So meaning to say, it will be like this. The extension, this is the distance. mgh, this is the distance that has been fallen, the distance that mass has fallen. It is h plus x. So meaning to say potential energy, mg into h plus x, which is mgh. Total distance fallen must be equal to the gain in strain energy. So for the strain energy, do not forget your formulas, guys. All the formulas that we had before, that you used before for the strain energy, you can equate that to your strain energy. Remember, we said our strain energy, in a normal calculation, as long as you're calculating the strain energy, it's half of what? Half of Fx. Also, strain energy can be given as F squared L over what? Over 2AE. Over 2AE, like this. You still remember our calculations for the strain energy. As long as we're talking of what? The strain energy. The formulas, these ones can be used. And also not forgetting that the extension, how do you calculate your extension? Remember, you're calculating extension from FL over AE, or you can use the phi A. Okay, it's going to be L over what? L over E. Okay, over E. You can use any formulas that we are capable of. All right, so this is for the extension. So using this extension, you can even substitute here. It's up to you. But from this case, it simply means this formula here can be written as the gain in strain energy, which is this one, half of what? Half of Fx, which is the same as this one from our strain energy calculation that we had before in our introductions. So this was F squared L over what? Over 2AE. The manipulations, we talked about this. So not going to talk about that manipulation, putting this X where the X is. Guys, we talked about that. So any of this can be equated. So also working with your formula sheet, like I always say that at the end of the day, it will be you and the formula sheet. You will see that they will give you this formula as mg into h plus x like this is equal to this. This is how they give you according to the formula sheet. But you're supposed to make adjustments now where x is needed, okay? Because you know that x is equal to what? You know that depending with the question, adjustments can be made. What is it that you are given on that question? But this is all that you have. As long you have to deal with what? A shock loss. So it will be now to say it is just a single bar. This one, there's not, it's just to this bar here is just, there's one. When they are now compounded, it is compound. You have to refer back to what we talked about compound bars. Additional of that. So we're not going to talk about the total strain energy because it's just a single bar. The strain energy that you calculate is just the strain energy. There are now bars that are connected. Then that's when you're going to talk of what? This total, the strain energy. Remember what we had before? Then we are given us an example, which is on Fig 2.11, 2.11. It shows a vertical rod. So this is what we have with length 1,5. So we've got the length of the rod. The diameter is also given 35 millimeters, and this rod is, okay, let's just try, see from the information that you're given. Calculate the maximum stress, this and that, all right? Let's try to figure out. So they gave us the length, and as you can see, it is rigidly attached at the top, and it is fallen for a height 0.4 meters onto the collar. That is what you're given, all right? So the original length, which is the length of what? Of the rod, the original length we are given, 1.5 meters, and also its diameter is corresponding 35 millimeters, just divide by 1,000 is going to be 0.035 meters. The rod is fixed to a top, which is the support in that case, at its upper end, and a rigid collar is secured, attached to its lower end, meaning to say we have that rigid collar there. A mass, which is part of our load, this mass falls freely through a what? 400 millimeter onto. So this is the height, the 400 millimeter. If you divide it by 1,000, it was going to give you 0.4. So we've got the mass, the 10 kilogram, the height, which is the 0.4 meters. So it falls freely. Once there's a falling part, we talk of what? The gravitational acceleration happening there. Calculate the maximum stress brought about the rod. If E, the Young's modulus, is given as 200 gigapascal. So they want you to calculate the maximum stress. What is the maximum stress? So how can I have this maximum stress, guys? We do understand it must be from the force over area. There's supposed to be a force to be considered and area to be considered. This is what our question is about. And we talked about this, guys. That's why I'm saying these formulas, guys, that we are seeing here, this part is just, this is the only idea of being a shock load and just being a single bar. But all other formulas, they remain the same. Which formulas are we talking about? All right, let me just go with you along your formula sheet, because we talked about these formulas on separate classes. If you consider from our formula sheet, all the formulas are still the same as we used to have before. Meaning to say, as long it is to be of a bar that you're talking about and material, issue of the stress, whatever that you talk about, all these calculations, they are going to remain the same. And also this one, like I said before, talking of the strain energy. The strain energy is equal to what? These are the formulas for strain energy. This one. Talking of what? The strain energy, but depending now the question, the F is going to be affected to say this and that. And now talking of what? This part that we have of the shock loads. This is the formula they are giving us there. So as you can see here, they equated to what? To the first one, because we saw there are two formulas representing U. So they represent to another. And also X, you know, is substitute. So these formulas, guys, they are there. You just have to link up the information that you're given. So in this case, it's true that we do need to calculate this maximum stress according to our question. Are we having the force? As we can see from here, we do not have the force. So this is not given. What about the area? Area we can calculate it because we have the diameter. So area, there's no effect there. Let's just say we have it because we simply know that our area is what? Pi d squared over 4. Just going to substitute there. So area is there, but the force is not there. So for you to find the force now, that is where you use this formula now to say, which part are you going to equate? Is this to this? Are we having extension? We are not having any extension. So it was going to be useless for us to equate to the extension. So we're going to equate this to this as it is given on our formula sheet. As it is given on our formula sheet. So this is going to be like this because we need force. So calculate F. Calculate F. So for you to calculate F, that is where now you're going to have your formula as mgx. Remember loss in what? Loss in PE, potential energy, is equal to that gain in what? In the strain energy. Okay? So if it is the gain in strain energy, therefore, what does it mean? It simply means we can use as it is from the formula sheet. Mg into H plus X is equal to F squared L over 2AE as it is given. But we do not have the extension. If we had this extension, this one, if it was there, this extension, guys, we were simply going to use half of Fx because there's no need for us to carry a lot of things. What we need is the force. So why are we going to use this one? If extension is there, the extension is not there. So it means also to use this formula, it will be limited. So what are you going to do? You are going to substitute the extension where the X is. So that's why you end up with your textbook, depending with the textbook that you are using, you end up seeing this formula instead of this X being written here. They will use it like this, mg into H plus X. They substitute the X null now as FL over AE like this. They're just substituting where the X is. And if you substitute that X here, that is where we got this one. So we're not going to equate to this one. When we substitute X, we're just going to equate straight to that one. So it is equal to F squared L over 2AE. So you find even some textbooks presenting like this. Then you say, okay, but the formula sheet is not like that. No, they just substituted the X, the extension. So this is still your X, this one, your extension. Remember your formula for extension, this one. So it can be like that, depending with your textbook that you're using. All right. But according to the universal formula for us, all of us, because exam is not about your textbook, it's about how they want you to have it. The formulas are there. So we're going to have that as X. But do not forget you're also given that. So you're just going to substitute just like the previous case. All right, let me quickly have this. So it was going to be mg into h. We saw that x is equal to what? FL over AE. So this is equal to F squared L over 2AE. That's the formula where the force is. That's where the force is, guys. This force here, that is where it is. So in order for you to calculate that force, that is, you have to think about this formula. As long as you're talking of what? The shock loss. So this one, we can calculate that F. How? Let's substitute, guys, and see. Miracle that's going to happen. So you're going to substitute all the information that we are given there. All that is applicable here. Are we having the mass? Yes, the mass is 10 times G, the gravitational acceleration, remember that's 9,81, into what? H. What is H representing? The height is fallen in meters. So that is 0,4 plus FL, that is force, which is the one that you need, times L. So we do not have the force, but we have L, the length, which is 1,5. So that is simply like times 1,5. Everything over what? The area. Remember I said we can calculate the area, pi d squared over 4. So that was simply going to be pi times d, the diameter, 0,035 squared over what? Over 4. So this is your area. Okay, so as you can see here, we are done like this. Substituted. Okay, we need E. Sorry for that. We need the E there. Area times E. So that's times E, which is 200 times 10 to the exponent of 9. See these things, guys, of using these softwares, you end up even missing something that you can see it's there on the formula. But anyways, that's it. So we're going to substitute everything, then equate to this part, F squared L. So this is going to be F squared times L. Remember, our L is still the same, 1,5. Everything over what? This is just 2AE, like what we had here. Just going to repeat, but yes, 2AE. So that's 2 times A, the A, which is our area, pi times D squared, 0,035 squared, everything over 4 like this. Okay, that's our area times E, which is our Young's modulus, which is 200 times 10 to the exponent of 9, the gigapascal. So this is what you are going to actually have from this understanding that we are seeing. So this is what you have, guys, from the understanding that we are seeing here. So how to simplify? How now to simplify? Okay. Because there we've got a lot of things. I want you to do this. I'm going to show you how to simplify on your calculator. So this is what you can simply do. I want you to simplify because this can be simplified. This one. This one. It can be simplified, this one. Just use your calculator to simplify this part, okay? I'm just going to try to show you guys. You simplify this part as it is here on your calculator as it is. Meaning to say, whatever that you're going to have there, it is going to carry what? F squared. It's going to remain with F squared. But you have simplified it. You have used your calculator there. So with that, simply divide by this one now. So after that, because here there are a lot of stages here, try my calculator can just misbehave. I know it. So by that, divide by this, which is outside of the bracket. Okay, so you're going to divide by this. 10 times 9,81. You also divide. Now you have an answer that is there. that answer that you're having there divided by what? 10 times 9,81. So you are going to see that these will cancel like this. You have a 1. And that 1 on this left-hand side will expand this bracket. So it will be 1 times 0,4, which is 0,4. 1 times this part here. So it will be just that part as it is. Also, just like how you simplify this, do the same here on this part. Simplify it, this part as it is. Here, simplify it as it is, this one. Simplify it. But the answer is going to be multiplied to f. So it will be plus. Once you simplify this, guys, you are going to get something like, on your calculator, 7,795 times 10 to the exponent of negative 9. Okay? Times 10. Actually, to get that, you can simply multiply your answer times 10 to the exponent of 9. Because it will be 0, 0, 0, 0, 0, 0. A lot of zeros that you get there, actually, on your calculator. So if you try to use that value that you're getting, boys, it will be 0,0000 up to the end. So what do you do to just have a better value? Target, you can target any number, -9, -10, okay? Multiply the answer that you're seeing there times 10 to the exponent of 9. The decimal that you're getting there is 0, what that you're getting here. Multiply it by 10 to the exponent of 9. Remember, guys, we talked about this. You want to convert to micro farads, you multiply by 10 to the exponent. Why am I talking of the farads now in strength? Okay, let's talk about something that is strength that we are used to in strength. You talk of the megapascal. What do? You multiply by the opposite, 10 to the exponent of -6. So that is the case of here. You want a -9. So you just multiply by the opposite times 10 to the exponent of what? Of 9. So guys, there are a lot of values. That's why I'm avoiding to use the calculator there so that it does not affect this whole presentation. But there is what? F. Remember? F there. So it's going to be having F. So whatever presentation that you have, you can multiply times 10 to the exponent of 10. But when you write here, you write as the answer that you get there, you use -10. You can use -11, you can use -2, depending with your textbook, all right? So this is equal to, this one, remember, we simplified this first, then that answer was divided by this. When you did that, the answer was going to be something like 3,973 times 10 to the exponent of -11. But it's having what? F squared. It was -11 on your calculator. Meaning, so you can even change this to -12 or whatever that you want, guys. It is your choice. But what is it that you can see? Remember, I want to calculate F. But look what is now. Look the weird question that we now have. What type of a question is this? F squared. We are now having a quadratic equation. Remember our quadratic equation. So you can write in the format ax squared plus bx plus c is equal to 0. Remember our quadratic equation, one side must be equal to 0. So this, we're going to start with it, 3,973 times 10 to the exponent of -11 f squared. We take this side, so it will be minus, okay, as it goes that side. 7,795 times 10 to the exponent of -9f. Okay, so this is where we are. We take the 0,4 that side, so it will be what? Minus 0,4. It will be a minus, which is equal to 0. So with this, we have got a normal quadratic equation that you use like this. So you can simply use a quadratic formula. Remember, x is equal to what? From our quadratic formula, x is equal to -b plus or minus the square root of b squared minus 4ac all over 2a from our mathematics. But we are talking of f, so it's no longer x. So it will be f instead, because we are solving for what? For the force. So we now write as f is equal to, instead of x is equal. There's nothing has changed. It's only that you're solving for what? You're solving for f. So you're going to substitute, guys, and solve your quadratic formula. F is equal to, this is our a, bx, this is our b, and this is our c. So it was going to be minus b, which is minus, that's a plus. Okay, just for the sake of us understanding, I'm just going to write the way that it was supposed to be, but you understand me there. 7, 795 times 10 to the exponent of -9 plus or minus the square root of b squared. This is our b, which is the -7,79 5 times 10 to the exponent of -9 squared minus 4. Our a, as it is, that's 3,973 times 10 to the exponent of -11. That's 4ac. Our c is what? Our c is -0,4. So this whole part is over what? This whole part is over 2 times a, where our a is given. That's our a, which is the 3,973 times 10 to the exponent of -11. Just like that. So this whole part here is under the square root. Yeah. This whole part is under the square root like that. So this is what we have. So you can use your calculator there. Just a normal quadratic. You start with a plus, you get your answer there. So if you start with the plus, you are going to get your f. If you start with the plus, your f was going to be equal to, and also here, guys, it's plus, it's minus, minus. So it's just a plus. There's no need here for you to write minus, minus. Here, I'm just showing you that what you are supposed to like. You have, or what your this is the display that your calculator is supposed to be displaying right now before you press the equal to. This is the display with a plus, just one sign. Remember, you start with one sign. So if you start with a plus, that's the answer is going to be equivalent to, you're going to get something like 100,437, something like that. 437,365,9, something like that. Or another f can be given as -100, -100,000 to 41.1665, like that. Okay, the other one was going to be a negative. So this is the first one, the first force, and this is the second one, the negative. So we're going to take the one with the positive. The negative is simply showing a compression which is happening. Okay, but in our case, it's not a compression. It's supposed to be an extension, because remember the mass had an impact with what at the collar having an extension. So it is being extended, going outside. So we're talking of what? The tensile force, the one that is supposed to be positive. The negative is for compression. So we're going to take our F to be this. So our F, therefore, is going to be, let's convert to kilo. Just divide by 1,000. Okay, it's going to be 100,437, which is kilonewton. This is the force that we need. This is the force that we need. The force, not the stress, the force that we need. Remember, we said we're going to need the force first here. So you see, guys, that's how they'll be testing you, playing with you guys in exam. They want you to understand this relationship. Loss in potential energy, gain in what? Strain energy. With this formula and adjustments made on the substitution of X, which is our extension, force can be calculated. And what's the purpose of this force? So that we can obtain the stress as we are given here, that the stress, which is the one that we need, now it can be calculated. So therefore, our stress was going to be, the maximum stress was going to be the force. Remember, we had that force, guys, from our answer. It was 100,473 437 times 10 to the exponent of the kilonewton. So it's force over what? Area. What is our area? Remember our area, we talked about this from the diameter, pi d squared over 4, and our diameter is 0,035. So that will be over area, pi d squared, 0,035 squared over what? Over 4. Just like this, it was going to give us the stress, which is the maximum stress as being asked on this question. And as we are calculating the stress, we know that this is megapascal. So I said simply multiply by 10 to the exponent of -6 so that your answer will be in megapascal. So by multiplying this whole part by 10 to the exponent of -6, guys, the stress that you're going to have there as the maximum stress will be in megapascals. And that is going to give us 104,392 megapascal. Just like that. So this is all about your shock loss, considering that it is affected to a single bar. So are you seeing the question that they just want you to answer there? It was calculate the maximum stress. But look, because of the force that is not there, we're now forced now to use these calculations. So in order for you to obtain the force, this equation, this one, you're going to use it in as much as you are working with the strain, this part of the strain energy, working with the shock loads. So I want you to know this and work with this. So as I said, because you are limited in your formula sheet, as I said before, your formula sheet, it gives you this. This is what your formula sheet is giving. So know your x, because you are given also that x here. Remember your x. You can make it the subject from here. We talked about making x the subject of the formula by cross multiplying. We ended up with our x being equal to what? To FL over what? Over AE. So they just substituted that x. Where x is, they substitute this. So in exam, and the formula is limited, and you do not know the exact formula, make adjustments also. And also your quadratic formula is given. X is equal to, and now we are no longer solving for x. This is what? The force. So you just like the force is equal. As long as you're talking of the force, yes, this is our quadratic formula, but as we're now calculating the force, that's why I was talking about those adjustments. So that's it, guys. Let's do revise and also try to understand how the formula sheet is given, how our textbooks are also giving us this information. But in as much as you are to refer your strain energy, do not forget, strain energy does not change. Its calculation does not change. Only that there's now loss in this, whatever that we equate to what we are used to. We are used to do this. But we are just equating the loss that happened in potential energy. That loss and the strain and the gain will be the same. So it's an equation from that formula. Guys, know that formula because they are going to be testing you that working with F, especially on F, because you need the force. There is no way, whether you're asked to calculate this, and that, as long F is needed, you are stuck because you need that F. So that's it, guys. Let us revise much questions, preparing ourselves for the exams which are ahead of time. Till we meet again.